Here's our next graphing question. And you're going to see things that repeat over and over again from the homework questions. So we're given a graph. Can you do calculus? That's derivatives, limits, and integration, and understand the question that's being asked and how to do it. So let's look. This is just the graph of a function, f, and it's from -4 to 6. And it consists of 4 line segments only. So we're talking triangles, rectangles, and trapezoids. Let g be the function defined by this. Very common that this is a style that it'll be defined as. Now, right away, I'm going to do this because I know there's going to be a question that's going to ask to do this. It's going to ask for the derivative. So right away, I'm going to take the derivative, and I have to know the fundamental theorem of calculus. So when you take the derivative of an integration, they cross out, and you just plug in x. There's no hook. In other words, that answer is just f at x. And then if I take the derivative again, then you take the derivative to both sides again, and this is going to be something I go back to understand this graph. So again, the derivative, integration, cross out. It's a plug-in question. Done. The next derivative is easier. I'm going to go back to that when I need to. Okay, on what open intervals is g concave up? So g, that would be the second derivative. So we're going to write down what we're looking for. So I understand that's when the second derivative is concave up. I'm writing it down so I show the people who's like grading it. I understand. Second derivative, when it's positive, that means concave up. Where is the second derivative positive? So I look off the graph and I'm looking at the derivative of this graph. So in other words, I'm looking at increasing and decreasing. So this is concave up when this is increasing. Sorry, when f is not increasing but positive, I should say. So where on the graph is the derivative positive? Where is it increasing? So from -4 to -2. And where else is it increasing? No, right here, from 2 to 6. You don't even have to write beautiful sentences, but you have to show the math and then what the answer is. B. Let P be the function defined by this. So I'm going to write it down. And then it says find the derivative. So step 1 is, do you know how to take the derivative with this? You should notice it's a product rule. What is that? That's the first times the derivative of the second plus the second times the derivative of the first. Done. You get a point for that. Then you're going to plug in 3. No point for this yet. Then we have to evaluate it. Then there's a point. So everywhere there's an x, I plug in 3 and then go for it. So do I know what g at 3 is? So I look again at what does g at x equal? Like what's the equation? So I'm going to plug in 3 and solve it. So on the side, I'm going to integrate from 0 to 3. Now I know off a graph what that will mean is to find the area from 0 to 3. So from 0 to 1, there's 1. Here's another to 2. And I want you to notice that the area above matches the area below. That I don't even care what the area is. That's 0. And then to 3 means this is the only part left that I haven't done yet. So these two are 0, and then this is what's left. So I notice the area is below. It's negative. I know it's a trapezoid, so find the area of the trapezoid. So what is the base? So it's 1/2, first of all, and the base is 1. And then the 2 heights we add up. So that's 4 plus 3. So altogether, that's -7 over 2. There we go. There's the first one. Okay, what's the derivative at 3? That's a little bit easier. So this is the function. The derivative, where's 3? There's 3. The derivative means what's the slope at there? If it was f at 3, then it's just the y-coordinate. The derivative at 3 means find it. What's the slope? That's what derivative means. So that's up 1 over 1. That's just 1. Now the next one. What's f at 3? Well, we just said that's just the y-coordinate. So if I go to the graph, f at 3, what's the y-coordinate? It's -3. And then what's the derivative at 3? So remember that the derivative means f at x. So if I say what's the derivative at 3, it means the same as f at 3. They mean the same thing, meaning the same thing I just did. So at 3, what's the y-coordinate? And that's it. You don't have to simplify it because I'm not comparing answers. There's no reason to go further than that. Part C. I'm going to write it down. A limit question while looking at a graph. It's a ratio. So step 1 is to separate the ratio. The numerator. That just means what does g at 2 equal? Did we do g at 2? So I first looked to see, did we do g at 2? Did we already do that work? I don't see it. So on the side, what does that mean? So I have to go back to what g at x equals again. So again, g at x is this. So plug in 2. And I'll do it down here. We're integrating from 0 to 2, which means the area, it's proper. So I don't have to worry about putting a negative first. And then what is the area from 0 to 2? Remember we said they are the same area, the same triangle. So that answer is 0. So the same area above is below, positive and negative, it's 0. Okay, how about the denominator? Write that down. So if I plug in 2 here, the answer is 0. This is indeterminate. So I'm going to write down the limit again. Now I'm going to take the derivative of the top and bottom. Now I know it's no longer indeterminate because if I plug 2 in the denominator, I already have an answer. 2 times 2 take away 2. Now, what's the derivative at 2? What does that mean? So again, this is my key. The derivative at 2 means the same as f at 2. They mean the same thing. So the function at 2, what's the answer at 2? And the answer is -4. And that's it. I don't have to write anything further. All right, you got one more question and we're done. D. Find the average rate of change from -4 to 2. So to do that, I'm going to first just subtract those numbers. That's my bottom, -4 to 2. And for G, I have to understand that I'm finding these values. So just setting it up is good. On the side, we can do it. So G at 2, what does that equal? Did we already do that one? We just did that one. That's 0. I know that we just did G at 2 because it's right here, and G at 2 equals 0. That's common too, where you've already done the work. Don't do it again. It's there. It's 0. Okay, how about G at -4? Have I done that work? So if I haven't done the work, it's integrating from 0 to -4 following the formula that was given. So again, I'm using this 0 to -4. It's improper or proper. It's improper because the bottom number is bigger. So we start with a negative parentheses. And then what's the area from there? So if I'm finding this area, I see a triangle. So this triangle, half the base times the height of it, which is 6. And then I see a trapezoid. So the base of that trapezoid is 2. Again, a trapezoid starts with 1/2, the base, and then we add the 2 heights. So one height is 6 and the other 4, so 6 plus 4, that's 10. Now I need to simplify this because of the work I still need to do. So it's negative. Half of 12 is 6. 2 times 10 is 20. Half of 20 is 10. So this is -16. So I'm going to come back here. So G at 2, that's 0 subtract -16, and then 2 plus 4, or keep it the same as 6. So this answer, and we don't even have to simplify it, is 16 over 6. We just found the AROC. Then the second question is, does the mean value theorem guarantee an answer from -4 to 2? And for which that is an average rate change, and then justify your answer. So for this function, for g, is g continuous? So could you put in any number and get an answer? Can you take the derivative at g throughout and get an answer? And the answer is yes. So how do we write that down? So the mean value theorem does guarantee a value because is both continuous and differentiable. That's the key. So you get a point for one and a point for the other. It always adds up to 9. So they were looking at, can you find the average rate of change? Do you understand why? Don't even look for it. So you're not asked to look for it, but why would you get one if you did? That's it. And again, less than 15 minutes. Beautiful. Mr. G Math, over and out.